On September 15, 2017, billions of miles from Earth, a faint stream of data blinked across the Deep Space Network antennas in California, Australia, and Spain. This was Cassini's last transmission, and it revealed a message that NASA never explained. NASA's Cassini spacecraft had spent 2 decades traveling through space and orbiting Saturn, sending back discoveries that reshaped planetary science. In those last moments, Cassini dove into the giant planet's atmosphere and transmitted its swan song. Today, we'll unveil the whole story. The story of the Cassini-Huygens spacecraft. In October 1997, after years of planning and international collaboration, NASA launched the Cassini-Huygens spacecraft from Cape Canaveral aboard a Titan IVB Centaur rocket. The mission was a joint project between NASA, the European Space Agency, and the Italian Space Agency, designed to explore Saturn, its complex ring system, and its diverse collection of moons. At launch, the spacecraft weighed more than 5,600 kilograms, making it one of the heaviest interplanetary probes ever sent into space. It carried 12 scientific instruments aboard the Cassini orbiter and an additional 6 on the ESA's Huygens lander, which would later make history by descending through the atmosphere of Titan. Cassini's journey lasted nearly 7 years before it entered Saturn's orbit in July 2004, marking the start of a mission that would redefine our understanding of the outer solar system. This was a historic moment, and it had not come easily. This story cannot be told without first stepping back to understand the moment in history from which it emerged. By the late 1980s and early 1990s, the Cold War-era space race between the United States and the Soviet Union had ended, leaving behind a dramatically different landscape for space exploration. With no geopolitical contest driving the urgency of missions, NASA began shifting its priorities toward long-term scientific discovery and international cooperation. Saturn, long a target of fascination since the flybys of Pioneer 11 in 1979 and Voyager 1 and 2 in the early 1980s, stood out as the next great frontier. Those earlier missions had revealed tantalizing mysteries, such as Titan's thick orange atmosphere, the intricate structures in Saturn's rings, and the possibility of ocean worlds hidden beneath icy surfaces, but they were quick reconnaissance missions, not extended studies. Scientists wanted more than glimpses. They wanted to stay, orbit, and probe. In 1982, NASA and the European Space Agency convened to consider a joint planetary mission. Out of those early conversations grew the idea of combining a Saturn orbiter with a Titan lander, a concept that evolved into what would become Cassini-Huygens. The mission reflected a new era in space science, one where collaboration across nations was as important as technological ambition. NASA would build the Cassini orbiter, ESA would design and contribute the Huygens probe to land on Titan, and the Italian Space Agency would provide the crucial high-gain antenna and other components. This was an unprecedented alliance. However, funding for Cassini faced challenges in the US Congress, with critics labeling it too costly. The final mission price tag reached about $3.26 billion, spread among NASA, ESA, and ACI. But defenders argued that the scientific rewards would be immeasurable. By the early 1990s, momentum was unstoppable. Cassini-Huygens was to be one of the most ambitious interplanetary missions ever attempted, carrying state-of-the-art instruments that could study Saturn's magnetic field, atmosphere, and rings with unprecedented precision, while also examining its moons up close. On October 15, 1997, after nearly 2 decades of conception and design, Cassini-Huygens lifted off from Cape Canaveral, Florida, aboard a Titan IVB Centaur rocket, the most powerful U.S. launch vehicle of the time. At launch, the spacecraft weighed more than 5,600 kilograms, making it the heaviest interplanetary probe ever built. Its sheer size reflected its complexity. Cassini carried 12 scientific instruments, including cameras, spectrometers, magnetometers, and plasma detectors, while Huygens carried an additional 6 instruments designed to probe Titan's mysterious surface and atmosphere. The spacecraft also included one of the largest interplanetary radio antennas ever launched to transmit massive amounts of data across nearly 1 billion miles. But the challenges were far from over. Getting Cassini to Saturn required ingenuity and patience. A direct flight would have been impossible with the available rockets, so mission planners charted a trajectory using multiple gravitational assists. Cassini slingshot past Venus twice, in 1998 and 1999, swung by Earth in August 1999, and passed Jupiter in December 2000, using each flyby to build the momentum it needed for the long haul. These encounters also provided opportunities for bonus science. During its Jupiter flyby, Cassini captured nearly 26,000 images and studied the giant planet's atmosphere and magnetosphere. On July 1, 2004, after nearly 7 years and 3.5 billion kilometers of travel, Cassini finally entered orbit around Saturn. Its arrival was marked by a tense sequence of maneuvers, including a 96-minute engine burn that had to succeed or the spacecraft would sail past the planet into the abyss. When mission controllers at NASA's Jet Propulsion Laboratory received confirmation that Cassini was securely in orbit, applause and relief swept the room. This was a historic milestone, making history in planetary science. Cassini had become the first spacecraft to orbit Saturn. The planet had remained a remote and enigmatic icon in the night sky for millennia. Cassini's arrival also set the stage for Huygens' triumph. On December 25, 2004, the probe detached from the orbiter and began its 3-week journey toward Titan. On January 14, 2005, Huygens descended through Titan's thick atmosphere, parachuting for 2 hours before landing on the surface. The probe transmitted images of river channels, floodplains, and pebbles made of ice, revealing a world eerily reminiscent of Earth but dominated by liquid methane and ethane instead of water. It was humanity's first and only landing in the outer solar system. The detection of towering plumes of water vapor and organic molecules erupting from Enceladus, first observed in 2005 by the spacecraft's instruments, suggested the presence of a global subsurface ocean beneath its icy crust. This was groundbreaking because it provided the first compelling evidence that a small moon of Saturn might harbor conditions suitable for microbial life. Before Cassini, Enceladus was considered an unremarkable ice-covered body, and no mission had been able to probe its geophysics with such precision. By flying directly through the plumes, Cassini's instruments, such as the ion and neutral mass spectrometer, analyzed their composition, detecting water, carbon dioxide, methane, ammonia, and complex organics. Yes, the very building blocks of life. The mission also transformed our understanding of Titan, Saturn's largest moon, which is larger than Mercury and had long intrigued scientists because of its dense nitrogen-rich atmosphere. Cassini, along with the Huygens probe, revealed that Titan possesses stable lakes and seas of liquid hydrocarbons like methane and ethane, making it the only other world in the solar system with standing liquid on its surface. Radar mapping pierced the thick orange haze that had obscured Titan from telescopic observation, uncovering vast dune fields, river valleys, and even evidence of rainfall. Cassini also allowed scientists to observe Saturn's atmosphere and ring system in unprecedented detail. Its cameras and spectrometers documented colossal storms, seasonal variations, and atmospheric dynamics that could never have been studied during a brief flyby mission like Voyager in the 1980s. For instance, Cassini captured the massive storm of 2010 to 2011, which wrapped around the entire planet and demonstrated how energy builds and erupts within Saturn's deep atmosphere. The mission also provided high-resolution images of the planet's hexagonal jet stream at its north pole, a geometric weather pattern unlike anything else in the solar system. The rings of Saturn were revealed by Cassini to be complex and ever-changing systems shaped by the gravitational influence of nearby moons. Cassini's instruments measured ring particles ranging from tiny dust grains to house-sized boulders, and it captured striking geometric wave patterns caused by orbital resonances with moons like Mimas and Pan. Before Cassini, such features could only be glimpsed in low-resolution images. Now, scientists could study them with precision. Over its 13 years in orbit, Cassini conducted 294 orbits of Saturn and completed 162 targeted flybys of its moons, returning more than 450,000 images and over 600 gigabytes of data. This immense archive transformed planetary science from static snapshots into a dynamic chronicle of seasonal and geological change in a complex planetary system. Before Cassini, most of what scientists knew about Saturn came from fleeting glimpses during the Voyager flybys of 1980 and 1981, which, though groundbreaking at the time, could not provide sustained, in-depth study. Cassini's longevity made it possible to track changes across years, observing how Saturn and its moons evolved over time. This had never been achieved before for any outer solar system body. But as with all good things, this too came to an end.